Hello, my name is Sean Fitzgibbon and welcome to this video in which I'll give you an introductory tour of diffusion imaging. Firstly, I'm going to talk about what diffusion is and what we mean by diffusion in this context. And I'm going to talk about diffusion weighting in MRI, that is, how do we achieve the diffusion weighted or diffusion coded signal in MRI. So what do we mean by diffusion? Well, what we mean by diffusion in this context is actually Brownian motion. We have water molecules that are not at absolute zero and are therefore moving around due to thermal energy, which is converted to kinetic energy. They bounce into each other and as a consequence end up taking a random walk in space over time. Thus we are talking about thermally driven random motion of water molecules. What we measure is how far on average a bunch of molecules will move away from the start point after some time. Einstein came up with an equation for this, which describes the mean square displacement for an ensemble or group of molecules. The two important terms here are the diffusion coefficient d and the time t. The diffusion coefficient is a scalar value that tells you how easily water moves around in that medium. And time is important because the longer we wait, then the greater the likelihood that the water molecules will have moved further from the start point. So the average displacement we measure is dependent upon both the diffusion coefficient and on time. So why are we interested in water diffusion in the brain? Well, we're not interested in water diffusion in and of itself. Rather, water diffusion is interesting because it tells us something about the local microstructure of the tissue. For example, in a part of the brain where we have free diffusion, such as the CSF, where water diffuses freely and equally in all directions, we would expect to be able to measure water molecules a long way from where they started. So diffusion in this tissue is isotropic because it moves equally in all directions. However, in grey matter, where we have lots of cell bodies, these cell membranes become an obstacle to diffusion. Water molecules can still move in any direction, so it is still isotropic, but the barriers mean that there is a smaller likelihood that a molecule will move a long way from where it started. So we would have less diffusivity in grey matter compared to CSF, which tells us something interesting about the structure of the grey matter. More interestingly, in white matter we have bundles of axons, many of which are myelinated. Both the axonal membranes and the myelin sheets greatly reduce the movement of water perpendicular to the axons, whereas along those axon bundles, water diffuses quite freely. This sort of diffusion, where water molecules cannot diffuse freely in all directions, but rather have a preferred direction of diffusion, is called anisotropic. So by observing the diffusion of water molecules in the brain, seeing how easily they diffuse, and if they have a directional preference, we can learn something about the local microstructure of the brain. So, the water in white or grey matter moves around less than we expect given the true diffusion coefficient of water. We refer to this reduced diffusion coefficient that we actually observe as the apparent diffusion or apparent diffusion coefficient, which is often shortened to ADC. How much this apparent diffusion is decreased from the free diffusion will depend on the diffusion time. To illustrate this, in the top plot we have the unrestricted movement or free diffusion of a molecule with position on the y-axis and time on the x-axis. Delta x is the distance this water molecule has travelled from the origin at a certain point in time. In the lower plot we have the same thing but with restricted diffusion due to a barrier. If we were to measure this diffusion at time t here, then the restricted diffusion would look exactly like the free diffusion. Whereas if we measure this at a longer time, the free diffusion and the restricted diffusion no longer look alike. So how do we measure diffusion? Well, this is an illustration of a diffusion pulse sequence. It builds upon a spin echo pulse sequence, which has the 90 and 180 degree pulses to give a T2 weighted contrast. But the important thing is that we add on top of that a strong magnetic gradient before and after the 180 degree pulse. The first gradient, if applied in the x direction, will cause spins on one side of the brain to precess faster than on the other side of the brain, which causes them to get out of phase. The second gradient is designed to exactly cancel the effect of the first one, so spins that are slower catch up to the faster spins, and everything comes back into phase. And we are back where we started, which might seem like a waste of time. But importantly, this only holds true for spins that are stationary in space. When spins have moved, as is the case when water molecules have diffused, the second gradient cannot perfectly cancel the first, which means that those spins will still be dephased, and this will result in signal loss. So the diffusion gradients allow us to tag water molecules that are non-stationary over time. And so we end up with an image that has signal loss proportional to the degree of diffusion of spins in the direction of the diffusion gradient. And I've been talking about these spins moving around, but it is important to realize that the movements that we are talking about are very, very small, on the order of 27 microns. So we are sensitive to movement of only microns, which is the same scale as the microstructure that we are interested in. So in order to know what the signal loss due to diffusion is, we first need to know what the signal was to start with. So we start by acquiring this one image where we have no diffusion weighting, and this is the baseline image. Then we acquire a diffusion weighted image using the sequence I described. And then the ratio of these two is a measure of the signal loss, and that is what tells us about the diffusion in the direction of the gradient applied during the diffusion weighting. And the key point to remember is that the signal loss will only be in the direction of the gradient. When describing the signal loss due to diffusion in an image, we need to know two things. How sensitive is the sequence to diffusion, and in which direction are we sensitive to diffusion? The former, namely how sensitive we are to diffusion or diffusion weighting, is quantified by the so-called B value. This B value is dependent upon the gradient strength and the diffusion time. For stronger gradients, even a small displacement will lead to a larger signal loss, so we are more sensitive to even small amounts of displacement. And the longer we wait, the longer the spins have to move around, so the greater the diffusion weighting. Here we have multiple images with different diffusion weightings. The first is B equals 0, and this is the baseline image where we have no diffusion weighting at all. At B300, you can see we start to get some signal loss. At B1000, we already have a lot of signal loss, and so on through the B values. Now, in order to get sufficient diffusion contrast, we would like to have as large a B value as possible. And there are two ways of achieving this, either having stronger gradients or having a longer diffusion time. But if we make the diffusion time too long, there will be more signal decay and therefore less signal, and as a consequence, poorer signal to noise. Therefore, if we want to have big B values, we need to have strong gradients, and this is why diffusion weighted imaging puts such high demands on our scanners. So we have established that diffusion contrast is modulated by diffusion weighting, but more interestingly, diffusion contrast is also modulated by gradient orientation. As I have already mentioned, the signal loss measured is proportional to diffusion in the direction that corresponds to the diffusion gradient. We can put the diffusion gradient on in numerous different directions, and there will be signal loss wherever there is diffusion in the corresponding direction. So we have the B0 on the left, and if you look at the corpus callosum in the yellow box, you will see we have a strong signal. Then we apply a diffusion gradient with a B value of 1000 in the X direction, so left to right in the first B1000 image here. And you can see here in the corpus callosum, where water molecules diffuse easily along the axons from left to right, there is a near complete signal loss. If you apply the gradient in the Z direction, as in the last image, which is coming out of the screen, you have an almost completely preserved signal in the corpus callosum, because there is almost no diffusion in the corpus callosum in the Z direction. So we can build up information about the direction of local diffusion in each voxel by using many different diffusion gradients with different orientations. And once we figure out what direction water diffuses in white matter, we can infer the direction of axon bundles. A typical diffusion-weighted MRI protocol looks something like this. We acquire one or more B0 images, which are the baseline image that tells us what the signal is in the absence of any signal loss due to diffusion, and a number of diffusion-weighted images with diffusion gradients applied in multiple directions. This plot here is showing the signal intensity of a voxel in CSF over volumes in a typical diffusion acquisition. These two high-intensity volumes are the B0. You can see that there is a big difference between the intensity of the B0 and the diffusion-weighted volumes. That is because in CSF, water molecules diffuse very easily and freely in all directions, which results in considerable signal loss compared to B0. You can also see that for all of these different diffusion-weighted volumes acquired with different direction diffusion gradients, we have roughly the same signal. And that tells us there is no preferred direction of diffusion. Water in CSF diffuses equally easy in all directions, and we refer to this as isotropic diffusion. However, if we look at a white matter voxel, firstly we see that the difference between the B0 and the diffusion weighted signal is not as big, and that is because we have restricted diffusion, so there is less signal loss. Secondly, there is a lot of variability in signal across the diffusion in the different directions, and that tells us that diffusion in this voxel does actually have a preferred direction. So, in summary, images acquired with a gradient along direction x have contrast that is sensitive to diffusion of water molecules along direction x. When diffusion occurs, signal is attenuated compared to no diffusion weighting. In white matter, measurements are anisotropic because there is a preferred direction of diffusion. In grey matter and CSF, measurements are roughly isotropic. Thank you.